Today in this video we're going to be going over deepfakes and explaining how they work and include code at the end so you can make your own deepfake. So what is a deepfake? A deepfake is a face swapping algorithm that uses neural nets to map out one face onto the other. And we can see in this example we have a real picture of Robert Downey Jr. on the left and a computer generated Elon Musk on the right. And what we're looking for is not only to have the realistic Elon Musk on the right, but we also want to map out the facial features from one image to the other. So this means that face A is looking the same direction as face B, their mouth is open at the same time, and maybe their eyebrows move up and down at the same time. So how does the neural network do this? Well, we'll start by reviewing autoencoders. So this is an autoencoder. It's very simple, it just has three main parts. The first part is the encoder. The encoder works just like a normal convolutional neural network. It takes in an image and compresses it down and then flattens it out the end and turns it into a vector. This will look familiar if you have ever done classification with the CNN. Okay, so the next part of our autoencoder is the bottleneck layer or the interlayer. The interlayer is just simply a fully connected or dense layers. And what this will do is give us a compressed representation of our data. Finally, we have the decoder layer. The decoder does the exact opposite job as our encoder. It takes in a vector and turns it back into our original image. So the goal of our autoencoder is take input X and reconstruct the original image as best as possible. So why do we use autoencoders? What we want is this middle layer. We want an abstract representation of our data, and we'll be using this abstract representation when making our deepfakes. So you might be thinking that deepfakes are made by using two autoencoders. We train one autoencoder on face A and another on face B. Then we encode face A with the first autoencoder, then decode face A with the second decoder. Well, this is almost what we'll be doing, but not quite. And there's some problems with that, and let's go over that right now. What we're seeing here is two autoencoders trying to encode the same data, images of handwritten digits. The labels are color-coded, so yellow represents the number 6, red represents number 8, and so forth. We can see even though these neural nets are given the same data, they encode it very differently. So how do we fix this problem? It's simple. We use a shared encoder and interlayer. This is the architecture of the deepfake model used by Deepfakes Labs. As we can see, there is a shared encoder and interlayer where both images A and B enter, and then we see these images being decoded with their own decoder. There are a couple things we won't be covering in this video. One is discriminator loss. This is an optional adversarial loss that can be used to give the image a better quality. The other is the predictive mask. That helps improve with the face swapping. Okay, now that we have an intuition on how the deepfake model works, let's jump into the code. Okay, so let's start off with going over our encoder, which is going to use these downscale layers. In the downscale, it's going to consist of these convolutional layers, a batch norm, a leaky ReLU, and a dropout. Now for our decoder, we're going to use these upscale layers, and it's going to be the same thing except with a transpose convolutional layer. This is going to kind of expand our image instead of compress it. And we'll be doing right after that the batch norm, a leaky ReLU again, and a dropout. So we're going to use a leaky ReLU in this case instead of regular ReLU because leaky ReLUs work better with smaller data sizes. And the dropout is going to be used to help with normalization. Okay, so if we look at it all together, this encoder is just going to consist of these downscale layers and then flatten it out. And then it's going to go into this interlayer, which is just going to be simple fully connected layers. We're going to be using 3. And then we have our two decoders that are going to be the exact same. First thing, we unflatten them, put them into a square image, and then we're going to run our upscales. Now I also include these ResNet blocks. It can be used to kind of improve the quality of the output, but it's optional, I guess. Okay, let's go in over the training loop. Let's grab our data set, and this is just going to be faces that we're going to be using. We have one for A and B, and we're going to keep running it, and then so for image A, we're going to make sure we're using the version A or decoder A, and then loss B. We're going to send in images B and then use the second decoder. And each time we're going to get the output, calculate the loss, and then do a optimizer step. Now for the loss, I'm just actually using the SSIM loss because I think it gives a better better result. But also included is the discriminator loss, which I don't use. I didn't find it gave me better results or anything like that. So then we save it, and that's it. And then we can reconstruct the images when we send in images A, and then we use version B.